Hello everybody! Today we're going to tackle Module 12 on page 383 in your textbook, the gas phase. We're going to cover all the way to ideal gases today. This module covers the following. We're going to have a definition for pressure, Boyle's law, Charles' law, ideal gases, Dalton's law of partial pressures, alternative statements of Dalton's law, the ideal gas law, and using that ideal gas law in stoichiometry, which is chemistry. So it's all about the gas phase. Here's one definition of pressure that is used in physics. It's not the one we're going to be using for chemistry, but you need to know it. And if you take physics next year, you're going to be using these quite a bit. So pressure, P, is the force divided by the area in which that force is being applied. Here it is. You have an area on an object. There's a force applied on top of it. And that combined is pressure. But chemists do not use this equation. So we're going to see in a minute what pressure is when we're talking about gases. The units for pressure, one of them, you're going to see several in chemistry. But if you were doing physics, you will be working with pascals. PA, named after the person who kind of came up with these. So the Pascal is the unit for force, which is in newtons, divided by the unit for area, which is meters square. Not gonna use that one. When we're doing chemistry, we need to think about pressure a tiny bit differently. Gas pressure, here you have a gas that's a diatomic, it could be oxygen, it could be any other diatomic, like fluoride, is the force of the gas particles colliding with the walls of its container, or also at the collisions with one another, because the gas particles are moving around, they do bounce against the walls, they do collide with one another, and that together, the collisions with the walls and each other create pressure in that container. So you need to know the definition of pressure for physics, but also, of course, you need to know the definition of gas pressure when we're talking chemistry. You also need to know what we mean by atmospheric pressure. So we're now on page 384 in your textbook. Here is Earth. We have the atmosphere, which is all the gases in the air around us. And that's a layer. It's a layer of gases. Gases have mass. Gases are moving around. Gases create pressure on the Earth, represented by these arrows right here. Okay? So here's another little picture that shows you that. So what's atmospheric pressure? Well, it's the pressure. The weight of the air in the column applies a pressure on this area. So if you divide the collisions, the forces in which all this air is applying on top of this area, you get a number, and that is your atmospheric pressure. But we're going to learn that atmospheric pressure is different at different levels of this column. You'll see that in a minute in a different PowerPoint, and then we'll see how we determine atmospheric pressure. So here we go. The atmospheric pressure has to do with the weight of all this air on top of the area on the Earth, wherever you are, that's being applied on that area. That's what it is, okay? So if you were measuring the atmospheric pressure up here, okay, you only have this little bit of air pushing down on you, or pushing down on this air right here. So the atmospheric pressure right here is lower than the atmospheric pressure at sea level, because there's a lot more air pushing down when you are at sea level. So on top of a mountain, if you are measuring the atmospheric pressure at the top of the mountain, you only have all this air pushing down on the people on top of the mountain, the atmospheric pressure on them is lower than it would be if they were standing right here at the beach, because they would have a lot more air pushing down on them. And usually we don't feel atmospheric pressure very much. Humans do not. Although, if you go very, very high up a mountain, you already know that it's harder to breathe because we're not used to having so little air. But atmospheric pressure, for example, will affect how long pasta or dishes need to cook. The time changes if you are on top of a mountain versus if you are at sea level. But anyway, let's see. At sea level, the atmospheric pressure is said to be 1. So when you see 1 atm, that stands for atmospheric pressure, is calculated at sea level. Whatever that is, which is 14.7 pounds per inch square, that's how much pressure is being put on whatever is at sea level, you, the rocks, the car that's parked in the parking lot. It's 14.7 pounds per inch square. This is not in the metric units, but that's okay. You don't have to memorize these. But by convention, that's called atmospheric pressure of 1. And if you don't understand these, after you read the book and watch the video, ask me questions when we meet on Fridays. Pressure conversions, page 384. The 1 atmosphere, so that pressure, that gas pressure that is being calculated at sea level, okay? There are other units that we can be using to talk about atmospheric pressure. The torr, millimeters of mercury, and kilopascals. And remember that pascals was the newtons divided by meters square, so that's kind of the metric system. And you do need to know these because the problems that they're going to give you will be using different units. And sometimes they're going to ask you to convert from one to another. Let's see. These gauges right here are calculating the pressure in torrs. This one right here is a mercury barometer. So basically the pressure of the air is pushing on the mercury right here. And when it pushes, it only can go up through the tube. Okay, there's no air. There's a vacuum right here. So the air pushing on the mercury makes mercury go up. And this has little lines that allows you to read the ups and downs of that mercury in the tube, and that's translated into millimeters of mercury. And that was one way that people measured atmospheric pressure. Let's see. Now, Robert Boyle, there's a whole section in your book about this scientist. He's the father of modern chemistry. He's considered the father of modern chemistry, and there's quite a bit of information about him. I'm going to let you read it, his history. You need to know a tiny bit about him. But we're going to concentrate on the formula and what he said about gases. Okay? So let's see. He's best known for his law, Boyle's law, which we're going to apply to problems in a minute, which says that the volume of a gas decreases with the increasing pressure at constant temperatures. That's what he says. And you need to know what he said and how it translates into a formula and apply the formula. But we'll see that in a minute. Let's see. Here is his law. Let's explain on page 385. Figure 12.1 explains his law visually. So we have a gas inside a container. The temperature is kept constant, means it doesn't change. And what he said, he was doing experiments with gases, and what he said was that when the pressure increases, see, the pressure here is pushing down by putting weight on the container top. So there was 1, 2, 3, and now here's 1, 2, 3, 4. So the pressure has increased, pushing down. What happens to the volume? The volume decreases. That's what he said. He observed these. He was doing experiments, and that's what he saw. So another way of saying the same thing is pressure times volume equals a constant. So if pressure increases, volume has to decrease to keep it a constant. And remember that the temperature has to be constant, meaning it cannot change, because the temperature does affect the volume of a gas, and we'll see that in a minute. So that's one way of looking at his law. Pressure times volume equals a constant, so if the pressure increases, the volume has to decrease to keep it a constant. And you need to be able to explain this back to me. Here's another way of looking at his law, page 386. During his experiments, he was looking at the effect of pressure on the volume of a gas, while the temperature was held constant, so he did not change the temperature. He just wanted to see how pressure affected the volume of a gas. So he saw that if pressure increased, the volume went down, which is what we saw a minute ago, right here in this picture. You increase the pressure, putting more weight on top of the top of the container, the volume went down. It pushed down on the volume. If the pressure decreased, okay, then the volume went up. Let's go back up and see this. So now you remove one of the weights. There's less pressure. So what happens? The volume can expand up. It increases. So you can look at his law like this: pressure times volume equals a constant, or another way of saying the same thing is this: pressure 1 times volume 1 equals pressure 2 times volume 2. And this allows you to calculate whatever you're missing. So P1 is initial pressure, volume 1 is initial volume. If you change one of them, the other one has to change. So pressure 2 is the final pressure, V2 is the final volume. So to keep it constant, if this has to be constant, if you change if you change the pressure right here, okay, this is a new pressure, then the volume also has to change to keep it constant, to be the same. So if you knew 3 of these, you can calculate the 4th. That formula allows you to see what happens when you change pressure or volume. How does it affect the other? And you need to know this formula right here and apply the formula. And we'll see that in a minute. Page 387, some more history for you. Charles Long, he also studied gases. So just know that a bit about him, just read about him in the book. I'm not going to go over history about this man, but we're going to see his law and how to apply it. Now, what did he say about gases? He said that the volume of a given amount of gas is directly proportional to the absolute temperature, Kelvins, when the pressure is kept constant. So he was experimenting with how temperature affects the volume, and he kept the pressure constant. So you see the difference between Boyle and Charles. Boyle kept the temperature constant and wanted to see how pressure and volume related to one another. And Charles, on the other hand, kept the pressure constant. He was more interested in seeing how temperature affected the volume. And here it is, a representation in a graph. as you increase the temperature, and these are Celsius, okay, but we're gonna work with Kelvin, and you'll see in a minute why we work with Kelvin. As we increase the temperature, he saw that the volume also increases, and that should make sense to you. As you see this container right here with the lid on, there's no weights on top, okay, there's no changes in weights, so the pressure here and here is the same on top of the container, just the weight of the lid. So the masses of the gases never change either, because it's the same amount of gas. So as you hit, or he hit, the gas, it expanded. What do you do when you hit a gas? You give it energy. So they want to move faster. Moving faster means more collisions against the walls of the container and one another. So that's pressure. You're increasing the pressure. But you're also increasing the volume. There's no pressure right here. They're moving as far away from each other, pushing up, because there's nothing to keep it down. Just pushing up, trying to take as much space as they can, because you gave it energy in the form of heat. Okay. You need to know Charles' law. Explain it to me what it means. Here is the first formula. Volume divided by temperature equals a constant. It needs to be constant. So if the volume increases, the temperature also increases. If the temperature decreases, the volume will decrease. That's what it means. And K is the same C that we saw a minute ago. Your book uses C, but in some other books they use a K. It just means constant. Okay. Before we move on to a more elaborate Charles' law formula, we need to talk about extrapolation. Figure 12.3 on page 387. What is extrapolating? You need to know that. So it's following an established trend in the data, even though no data was collected for that region. So right here, you see this broken line right here. When you see broken lines right here, means that this information was extrapolated. The data was not collected for this region, but the trend, so if you use your ruler, put it on top of this, and you continue drawing, it looked like it would go this way. That trend is going that way. And the same for this line, and this line. But no data was collected here. This is just a very good guessing game. Usually extrapolation works. Sometimes it doesn't. But at this level, we're going to say that extrapolating just means follow that trend, even though you don't have data for it. This is what you think is going to happen because this is what it looks like it's happening, kind of thing. And here you have a temperature again versus volume. It's in Celsius for right now. Remember that minus 273.15 degrees Celsius is your 0 Kelvin. Basically, we have never been able to reach 0 Kelvin. Some of these temperatures are too hard to achieve. So we cannot collect information there. But not only that, think about it. What is volume? Everything that's matter has volume. Everything, that's what we learned in the first module in this course, is that matter, by definition, occupies space, has a volume. Gases are considered matter. They have little atoms and molecules in there. They're far apart from one another, but you can push them down close together, and they do have a mass, and they are matter. They have volume. You can never ever reach a 0 for volume because they exist. So they have to have some kind of volume. Okay? So know that too. You need to be able to explain why volume cannot reach 0. Because gases have volume. All of them. You can compress them quite a bit, but not to 0. Here's another one. It's the same thing. 0 degrees Celsius is 273 degrees Kelvin. Absolute 0 degrees Kelvin is minus 273 degrees Celsius. We have never been able to reach this temperature. The closest we have been able to reach is 0.1234560 Kelvin. So very close to 0 kelvins, but not quite. Okay, and know this: volume cannot reach 0 because all matter has a volume, and gases are matter. So you need to be able to explain this back to me, understand it, and explain it back to me. So here is Charles' law formula, the same one we saw before. Okay, volume divided by temperature is a constant, but another way of saying that is this: if you change the volume, you also are changing the temperature. So by knowing 3 of them, you can calculate the 4th. Whatever they give you allows you to calculate whatever you're missing. So you can see how temperature affects volume with this formula, and we're going to apply it in a minute. Page 391, the combined gas law. Well, you're combining both Boyle's law and Charles' law. So pressure times volume, this is Boyle, but down to divide the volume divided by the temperature, that's Charles. This is a combination of the two laws, still true, is a constant. So if you change one of them, the other two also will be changing. And this allows you to calculate whatever you're missing. So if you want to know if you change the pressure and the volume, how it affected the temperature. If you change the temperature, how it affected the pressure and the volume, and so on. Whatever you're missing, you can calculate with this combined gas law. When using any equation in this module, you must use the Kelvin temperature scale. And the temperature in Kelvin, remember, if they give you the Celsius, you're going to have to convert it into Kelvin. I don't know why I have to tease, but that's okay. Temperature in Kelvin is the Celsius plus 273.15. That's what we're going to be using for this module. Think about it. Temperature goes at the bottom, is dividing. If you were using the Celsius scale, you could have 0. Remember that with Kelvin, we have never been able to reach 0. So you're never going to be dividing by 0. But with Celsius, if you were using Celsius, you could put a 0 here. And what does that mean mathematically? You cannot divide by 0. It's meaningless. So that's why we avoid any scale that would allow us to put a 0 at the bottom. Now, when you're doing this, when you're using this to solve problems, okay, you need to be very careful with the units. That's what the next slide was trying to say. Make sure that all the units match. So the units for pressure 1 and pressure 2 need to match. If you're working with atmospheres, both need to be in atmospheres. If you're using torrs, both of them have to be in torr, or Pascal, or millimeters of mercury. If they don't ask for a specific unit, you can use the units they give you, but they need to match. And the same thing for the units of volume. So volume 1 and volume 2, their units need to match. If you're using liters, milliliters, cubic centimeters, or cubic meters, they need to match. And you already know that for temperature, you're going to be using Kelvin. So how do we use all this information in a problem? Page 392 in your textbook. You have example 12.1, and then we're going to do 2 more. Let me read it first, and then we're going to solve it. Has 2 sections. Section 1, a weather balloon is filled with helium before it's launched. On the ground, the gas has a temperature of 25 degrees Celsius and a pressure of 1.0 atmospheres. The volume of the balloon is 4.5 cubic meters. As the balloon rises, However, the pressure and the temperature change, and it changes to 0.30 atmospheres and 15 degrees Celsius. What is the new volume of the balloon? So we're going to solve that first. And number 2, a gas is stored in a 3-liter container at a pressure of 453 torr. If the temperature stays constant, what will the pressure of the gas be if the volume is decreased to 0.75 liters? So let's go to the board here and try to solve this. Okay, let me get my pen, mouse, and here we go. So we need to make sure that we have information. We have two situations here. Okay, let me get my white. Here we have the balloon on Earth, so down, and then we have it up. Okay, that balloon goes both ways. Now let's collect the information where it belongs. So where the balloon is filled with helium before it launches. On the ground, the gas has a temperature. They give you a temperature. And I hope you notice that they give it to you in Celsius. And we know we're not going to be working in Celsius. We're going to be working in Kelvin. So we're going to have to translate that into Kelvin. And it has a pressure of 1 atmosphere. The volume of the balloon, so they give you also the volume of the balloon, is 4.5 cubic meters. As the balloon rises, it's going up, the pressure and temperature change. So the pressure now is 0.30 atmospheres, and the temperature has changed to 15 degrees Celsius. That's a 1. What is the new volume? So volume is your question. Remember that these are your 1s and these are your 2s. So before and after, sorry, I said 2 and I put 1. Okay, so your before and afters. So let's get that combined, the combined equation. What does it look like? It looks like this, which you're going to have to memorize. It's not very complicated though. And then we need to look at the unit to make sure that everything is in the units that you need. Let's see. Temperatures are not in the units that we need. That's bad. Atmospheres match. That's going to be good. And we can give the volume in cubic meters because it didn't say to give it in anything else. Okay. So let's see. The first thing I'm going to do is translate my temperatures. Temperature 1. So remember that we need it in kelvins. And all I have to do is add 273.15 to it to know my temperature in kelvins. So it's 25 plus 273.15, and this adds up to 288 Kelvin. What about temperature 2? So 15 plus 273.15 equals, let's see, I confused the numbers here. Let me change these. I didn't add it correctly because I'm copying these, but I copied it wrong. So the first one was 298 and the second one is 288 kelvins. So now we have the units that we need. They're asking for volume 2, so we're going to have to modify I like to modify the formula before I put the numbers in. Anything that's multiplying on this side is going to go dividing on the other side. So P2, this is gone. And everything that's dividing on the side that you're trying to isolate one of the, in this case is volume. Whatever is multiplying goes on the other side dividing, and here anything that's dividing goes on the other side multiplying. So extend these and you have your formula. I'm gonna erase it so I don't have to write it. Well, actually I'm gonna write it again because it looks prettier. So volume 2 is temperature 2 times pressure 1 times volume 1 divided by pressure 2 and temperature 1. So I have all the information to put in the formula. I'm going to do it in blue, and I'm going to do it on this side. So what's temperature 2? It's 288 Kelvin. That is multiplying my pressure 1, which I have, 1 atmosphere. And it's multiplying volume 1, which was also given to me, 4.5 cubic meters. Then I'm going to divide. By pressure 2, which was given to me, 0.30 atmospheres. And also on the bottom part is temperature 1, which needs to be in Kelvin. So it's 298 Kelvin. What happens here? The units are going to work out. The atmospheres are gone. The Kelvin are also gone. And you're going to be left with cubic meters. Put everything in the calculator. And then you'll see that your volume 2 equals 14 cubic meters. Okay, so this is 14. I should put it here, 14. This is the answer. And remember to square it so I can find it on your page. So what happened here? The volume went up because the pressure and the temperature decrease. Okay, so let's clear this and do the second section. And remember, if you have questions, ask. Modifying formulas is algebra, so hopefully you remember how to do that. It's just algebra. So what does it say? It says section 2, a gas is stored at 3 liters. What is that? That's volume. Okay, a 3-liter container at a pressure, so the pressure is given to you in torr here, 456 torr. Okay, if the temperature stays constant, so temperature 1 equals temperature 2, so this is not going to affect anything. Okay, what will the pressure of the gas be? They want to know pressure. This is 1. They want to know pressure 2. That's what they want to know if the volume is decreased. So volume 2 equals 0.75 liters. Okay, let me write again the formula. That's the one. When they say that something is constant, means that you can't ignore it. So basically what we're doing is, okay, if this is the same, I don't have to put it there. And you're left with this section of the combined law. Okay, so let's see, or the same as the void law to calculate pressure. Do we have everything we need in the right units, liters and liters? And I can give my pressure in torrs because you didn't tell me to do anything else. Okay, so I'm trying to find pressure 2. This is multiplying on this side. If I want to get rid of it, it will be going dividing on the other side because I'm dividing here and I need to divide there as well. So it will end like this: P1 volume 1 divided by volume 2 equals pressure 2. And now I have all the information to put in the formula to calculate my pressure 2 when I do it in blue. So pressure 2 equals pressure 1, 456 torr. My pen today it's not working very well, sorry about that. And my volume 1, which is 3 liters, divided by volume 2, 0.75 liters. Once again, the liters disappear. I put all my numbers in the calculator and that shoots out, let's see, 1.8 times 10 to the 3 torr. And this is pressure 2. So what happened here? As the volume decreases, the pressure increased, which is what we were expecting. Okay? Now, I want you to try extra practice problems number 1 and number 2. I'll give you the answer. If you don't get the same answer, I would advise you to try again. If you still don't know how to do this, then watch the video to see how it's solved. Remember that this is a video, you can pause it. So pause it here, try it on your own, check the answer, and then move on. So for number 1, so these are extra practice problems, okay? And I don't think I told you what page to find them in. I think the slide did tell you. It's page 380 in your textbook. So the answer for number 1 is volume 2 equals 1.4 liters. You got this? Move on. Number 2. Number 2, let's see. Also volume 2 equals 7.75 liters. You got this? Move on. It's the last section of the module for today. If not, try again or watch me solve these problems. So let's start with number 1. So number 1 reads like this. A balloon is filled with air so that its volume, I'm going to put it first, volume equals 5.6 liters. The temperature is also given to you, 25 degrees Celsius, which is going to have to change. It's then lowered into a vat of liquid nitrogen so that it reaches a temperature, so the new temperature is minus 196 degrees Celsius. Assuming that the pressure stays constant, so pressure 1 equals pressure 2. So I mean it's not going to affect anything, that pressure. What is the new volume? So remember that this section is 1, the new section is 2. You write down your formula. You eliminate anything that is constant. So in this case, you're going to eliminate the pressure. It doesn't affect anything because it's the same on both sides. You need to remember that temperature needs to be in Kelvin. So you need to translate those temperatures into Kelvin. So temperature 1 equals, remember that temperature into Kelvin is degrees Celsius plus 273.50. So put those numbers in your calculator. Let me erase this and put it directly here already. So my Celsius for number 1 was 25.0 degrees Celsius plus 273.50. And if I do that, that temperature is 298.2 Kelvin. I need to do the same thing for temperature 2. So it's minus 196 degrees Celsius plus 273.50. Do that, my next temperature is 77.2 Kelvin. So I have those now. Now, what are they asking for? Volume 2. They're asking for volume 2, so they're asking for this right here. I don't have it isolated, I need to have it by itself. So whatever is dividing on this side goes on the other side, multiplying. Okay, and then I can eliminate it from this side. And I'm left with, I'm going to write it pretty. Volume 2 equals temperature 2 times volume 1 divided by temperature 1. The new formula allows me to calculate volume 2. Just put the numbers in. What's temperature 2? 77.2 Kelvin. Multiplying volume 1, which was given to you. That was 5.6 liters. What's temperature 1? We just calculated right here. 298.2 Kelvin. Kelvins cancel one another. We're going to be left with liters, and that's where the 1.4 liter came from. That was the answer for number 1. Number 2. Let's read it for a sec. Number 2. A balloon is filled with helium. Once again, you can have a before and after. So a temperature, once again, they gave it to you in Celsius, 25. And a pressure of 755 millimeters of mercury. We have not worked on those yet. I'm going to move it right here. And let me see if I can make it a tiny bit cleaner. Yeah, okay. And what else? So that its volume, so volume 1 equals 6.65 liters. If then rises to an altitude where the temperature is 15 and the pressure is 625 millimeters of mercury, what is the new volume at that altitude? Volume 2 is our question. Great. I'm going to modify the temperature first. So temperature, remember to modify it, is the degrees Celsius plus 273.15. So I'm going to just give you the number, because you can put that in the calculator and just do it. What are the new temperatures? The first one is 298, and I'm sorry, but the mouse is not working very well today, Kelvin. And this one right here becomes 288.2 Kelvin. And you have used this formula to calculate that. Now everything is in the right units. What is the formula? P1 times volume 1 divided by temperature 1 equals P2 volume 2 temperature 2. What are they asking for? They're asking for volume 2. So I need to modify it. Everything that's multiplying goes on the other side dividing. Everything dividing goes on the other side multiplying. So I have a new formula. It looks like this. Volume 2 equals temperature 2 times P1, volume 1, P2, temperature 1. And I have all the information. I just have to put it in. So let me erase this section so I have some room to do that. Volume 2 equals, what's temperature 2? Well, it's 288.2 Kelvin. What's pressure number 1? 755 millimeters of mercury. And what is volume 1? 6.65 liters. And then I have to divide by what? Pressure 2, so 625 millimeters of mercury, and also multiply it by the temperature 1, which was 298.2 Kelvin. Okay, I'm gonna erase these. And what is that come up to? As you probably noticed, the Kelvin cancels a Kelvin, mercury cancels a mercury, and you're going to be left with the units of liters, which is what you want. Put that in the calculator and you get the new volume to be 7.75 liters, which is what we said at the beginning. So there you go. That's how you solve number 2. And if you still have problems, remember to ask me on Friday when we meet. Okay. Now we're going to finish this module. So if I can make this smaller. I'm having problems. Well, I think I can read these. Oh, there you go. But why it's not making? I'll just leave it like that. Okay. Ideal gases. The formulas that we have been applying and we learned about only work for ideal gases. So the only time that you can use these formulas is when you have an ideal gas. So So we need to know what an ideal gas is. An ideal gas is a gas that has the following properties, and you're going to need to memorize these properties. We're on page 394 plus in your textbook. For a gas to be ideal, the molecules or atoms that make up that gas need to be very, very small compared to the total volume available to the gas, because we want a large volume. Number two, the molecules or atoms that make up the gas must be so far apart from one another that there is no attraction or repulsion between them. Once again, we want that volume to be large. Number three, the collisions that occur between the gas molecules or atoms must be elastic. In other words, when the molecules or atoms collide, no energy can be lost in the collision. That's what it means to be elastic. So when they collide, because they do, they don't lose energy. Also, no energy can be lost when the molecules or atoms of the gas collide with the walls of the container. And all of this is to make the volume large. Okay. Okay. I managed to make this smaller, so hopefully you can see the whole slide. When do we have a large volume? So it's all for a gas to be ideal, that volume has to be large. And you already had a few things there about the size of the atoms and molecules, about temperature and so on. Okay? So here we go. When do we get that? Boyle's law is right here. So pressure 1 times the volume 1 equals pressure 2 times volume 2, and Charles' law, volume 1 times divided by temperature 1 equals volume 2 temperature 2, meaning it has to be a constant, and you can combine them to make the combined law. So what happens here? If you want the volume to be large, what does it mean in terms of the pressure? If you want this to be large, the pressure has to decrease. It needs to be small. In Charles' law, if you want your volume to be large, the temperature needs to be large or small. You tell me. Think for it for a minute, because I'm going to be asking you questions like these. Well, if you remember, what happens with temperature is that you're giving energy to the gas. And if there's no pressure, the volume will increase as you increase the temperature. You need to be able to explain things like this back to me. So you can get a large volume if you decrease the pressure and you increase the temperature. And here is a visual representation of what we just said. Okay, volume 1, volume 2. So there's more volume right here, which is what we want for our ideal gas. Okay, and we can accomplish this by increasing the temperature in this, or by decreasing the pressure on top. Now, you also need to know the definition of standard temperature and pressure. And you're going to see this in your book as STP, page 395. What is standard temperature and pressure? Sometimes the problem will say we're working at STP. And in your head, you need to be able to translate STP as 1 atmosphere of pressure and 273.15 Kelvin, or 0 degrees Celsius. That's a standard temperature, that's a standard pressure. Sometimes they will not give you the information in numerical form. They'll just say STP. So you need to memorize what that means. It means 1 atmosphere of pressure and 0 degrees Celsius, which is 273.15 Kelvin. A gas with a temperature that is close to or larger than 273 degrees Celsius, so larger than freezing temperatures, or close to freezing temperatures, but bigger, okay, not lower, and a pressure that is near or lower than the pressure you have at sea level will behave in an ideal fashion. Under those conditions, we can use all the equations in this module. And you need to know that you only can use those equations if you have an ideal gas that's behaving as an ideal gas. So let's do one problem to see how all of this is put together. Extra practice problem number 3 on page 380 in your textbook. Remember to pause here, and then we'll tackle that together. You try to do it on your own, and here we go. The answer for number 3, extra practice problem, is volume 2 equals 51 milliliters. So if you got this, move on. If not, keep watching. Let's erase these. Remember to read the problem carefully. It says a chemist collects, and they say 56.7 millimeters of nitrogen. So basically what they're giving you is a volume. So 56.7 milliliters of nitrogen gas at 25 degrees Celsius. So the temperature is also given to you, 25 degrees Celsius, and 740 torr. So what's that? That's pressure. Those are units of pressure. So 740 torr. What would the volume of the nitrogen be at STP? STP. That's your beginning. And now STP needs to be translated. What did we say STP stood for? Standard temperature and pressure. And what is that? It's something you have to memorize. So that means that the pressure, I'm going to put it here, pressure 2, is 1 atmosphere which means that our units are not the same. We're going to have to translate that into torrs probably. We're going to do that in a minute. And that also means that there's a standard temperature. What is the standard temperature? You had to learn that. And we're going to be working in Kelvins, so you need to memorize it in Kelvins, which is 273 Kelvins. Okay, great. And they want to know the new volume. So basically, you're going to be using the same formula you've been using all along. You just needed to remember what STP stood for. Then you needed to notice that we have atmospheres and torr, and that's not going to work. That here we have Celsius, which we're going to have to translate into Kelvin, and apply everything and put it in. So let's start with the temperature one. So temperature 1 equals 25 degrees Celsius plus 273.15. So if you do that, your new temperature is 298 Kelvin. Okay, great. So that is done. Torrs and atmospheres are not going to work. So what are we going to do? Change it. P2, 1 atmosphere. If you remember in the slide I gave you, and I said you're probably going to have to memorize this. So 1 atmosphere is 760 torr. Or you can just directly say, oh, this is 260 torr. Okay, but you also can use the factor level method to change it, which is 7.60 times 10. My goodness, my mouse today is not working. 10 to the 2 torr. Okay, so I'm gonna erase the yellow because we just calculated units in the correct unit form. I'm going to put down our formula for an ideal gas. Let me start all over. P1, B1, T1, P2, B2, T2. Okay. And then I need to find out V2, so volume 2. I mean that those two need to be moved to the other side. Multiplying goes on the other side, dividing. Dividing, other side multiplying. And now I have modified my formula to find V2, which is 2, P1, P1, P2, T1. Okay, so I'm done modifying my formula. I just need to plug everything in. So volume 2 equals 740 torr multiplying 56.7 milliliters multiplying 273 Kelvin and divided by 298 Kelvin multiplying 7.60 times 10 to the 2 torr. Now the torr cancel one another, Kelvin cancel one another. You're going to be left with milliliters, which is what you wanted, and that's where the 51 point sorry, that doesn't even look like a 1. 51 okay, milliliters came from, and you have solved number 3. Okay, so the only tricky thing in this problem, because you have done some problems already with this formula, was to remember what STP stood for: standard temperature and pressure, and that means a pressure of 1 atmosphere and a temperature of 273 Kelvin. And to remember that units need to match, so you need to change units when they don't match. And this is solved. Okay. So ideal gases. The pressure will be smaller or close to 1 atmosphere, so small pressure, and temperatures have to be bigger or close. It can be tiny, just bigger. It cannot be negative than 273 degrees Kelvin, which is the 0 degrees Celsius. Do not confuse standard temperature and pressure with standard conditions, because remember that when we do labs, we talk about standard conditions. Okay, and that is 25 degrees Celsius, because most rooms are kept at that temperature at 1 atmosphere. That's standard conditions, and we use standard conditions in lab situations. So do not confuse the two. Standard temperature and pressure are those two, and you need to memorize them. This ends the first half of module 12. Read the textbook, add to your notes if you need to, review examples, work on your own, correct as you go, study for your quiz. There was no labs, so you don't have to do labs this week, and then study for your test. I'll see you Friday.